Welcome everyone to the Formula SAE Weight, Center of Gravity, and Moments of Inertia presentation. Thank you for joining us today, and a big thanks to the SAE Detroit section in partnership with the SAE Carolina section for hosting this event. I am Matt Meyer, a General Motors EV propulsion engineer, a longtime SAE International Detroit section volunteer, and your moderator for this presentation. Before we start, I want to address a couple housekeeping items for this live presentation. All participants are automatically muted with their cameras off. We do encourage you to use the chat function to ask any questions you may have. You can start right now. I will take your questions and ask them to the presenter at the appropriate time. This presentation is being recorded and it will be posted on the SAE Detroit section YouTube channel at a later date. If you're already watching this on YouTube, please consider liking this video, sharing it with someone who might find it useful, and subscribing to our SAE Detroit section YouTube channel. You can find other past presentations related to the Formula SAE competition on the SAE Detroit section YouTube channel. You can also follow the Detroit section on LinkedIn, Facebook, X, formerly known as Twitter, and Instagram. And the last item, Darrell, if you could move to the next slide, please. The Detroit section will be hosting more live Formula SAE presentations and Detroit local student events in the coming weeks. If you'd like to join our future live presentations or any of our other events, please make sure to go to our section website at www.sa-detroit.org to register for these events. Today, we're going to be hearing from Darrell Hancock Jr., Senior Technical Specialist at Stellantis. This presentation will explain how to track and manage the weight of your FSAE car through the design process, including calculating weight distribution, center of gravity location, and moments of inertia. Welcome, Darrell. Thank you so much for being here today.
Okay, thanks, Matt. We'll go ahead and get started now. So today we're going to talk center of gravity, weight, moments of inertia. The agenda is there. We'll talk different kinds of weight, sprung versus unsprung, weight distribution of your vehicle, calculating the center of gravity location, calculating the moments of inertia of the whole vehicle, and then we'll talk a little bit about moments of inertia of your rotating parts, wheels, tires, brake rotors, half shafts, that sort of thing. Then we will talk briefly about how to measure the center of gravity of your vehicle and how to measure the rotational inertia of your components, your rotating parts in the car. Okay, so why is weight important? I think we probably all have some appreciation for that. Just to break it down a little bit, Newton's first law says force equals mass times acceleration. So Formula SAE is primarily about maximizing acceleration, whether it's longitudinal, braking and acceleration, or lateral cornering, right? So if we rearrange that first law, it says acceleration equals force divided by mass. So to maximize acceleration, you either have to increase the force that you're applying or reduce the mass. All right. So today we will talk about mass. And I'm going to apologize early. I'm probably going to use the terms weight and mass interchangeably, although they are different by the factor of gravity. So in metric, they're different by 9.81, by the factor of 9.81. But I will be a little bit loose and use those interchangeably. Obviously, when you're doing calculations, you need to make sure you're using the right value and the right units. Okay, so there's two types of weight in your car. There is the sprung weight, which is everything above the suspension, everything up here, the body, the chassis, the driver, the powertrain, the aero, everything that's on top of the springs, basically. And then there is unsprung weight, everything that's beneath the springs. So the wheels, the tires, the brake calipers, knuckles, uprights, whatever parts are down there on your vehicle. Could be the motors if you have in-wheel motors on an electric car. So there is kind of a third group of parts, those that connect one to the other. Control arms, half shafts, suspension links. And generally, we consider those to be half unsprung and half sprung. There are different rules of thumb out there. Maybe it's 2/3, but they're not a significant part of the weight. So whether you use 2/3 or half doesn't really make a big difference in calculations. So we'll talk a little more about why you need to make the distinction between sprung and unsprung mass. So sprung mass, again, that's the chassis, the driver, everything that's on top of the suspension. So it is a spring mass system. You have your suspension spring, the effective stiffness of that suspension spring, and you have some kind of a damper, a shock, or a strut. Then you have that unsprung mass, and it's also a spring mass system on the tire. The tire is acting as a spring, and the tire has a small amount of damping in it that's usually neglected. So you have two spring mass systems, spring mass damper systems that are vibrating. And usually we talk about that in terms of ride. In Formula SAE cars, ride is not a real high priority, but one of the effects of ride is the contact force between the tire and the road. And obviously we want to minimize the variation in that contact load to give the tire the best grip. So it's still important, that aspect of ride. And one of the key things to do that is to have a high ratio of the sprung mass to the unsprung mass. You want everything above the springs to be heavier than the unsprung mass. There's some rules of thumb out there. You know, there's an ideal 10-to-1 ratio. Very few vehicles achieve that. And your Formula SAE car probably won't come close to that. Because when you do all kinds of things to reduce the weight of your car, you're primarily focused on the sprung mass. But keep in mind that ratio is still important. Okay, and another distinction between the sprung and unsprung weight or mass, when you hit the brakes and your vehicle dives, it's the sprung mass that moves, not the unsprung mass. The tires remain in contact with the road. The load will shift, the diameter may change slightly because of the spring rate of the tire, but it's the unsprung mass that moves in both acceleration and braking. And then when you corner, again, it's the sprung mass that moves in roll. The wheels and tires stay in contact with the road, and only the sprung mass will move in roll. So that's a distinction there to keep in mind. However, when you corner and you're yawing the vehicle, you're turning the whole vehicle around a corner, the entire vehicle is moving, including the unsprung mass. So the whole weight of the vehicle is important in yaw, and the inertia of the vehicle. That's something that's frequently mentioned in Formula SAE. You want to reduce that yaw moment of inertia. We'll talk more about that later. Okay, so the next part of weight that we talk about is the weight distribution. And that's what percentage of weight is on the front axle. I put that in quotes because we don't have a solid axle, but on the front wheels versus the rear wheels. You can also talk left to right weight distribution, but it's generally pretty close to equal left to right, and we don't concern ourselves too much with left to right weight distribution. Front to rear, though, is pretty important, something you need to track and be aware of and manage. So I looked at the results from the June 2023 competition, and the front to rear weight distribution ranged from 39% front, 61% rear, to the other extreme of 53.3% front, 46.7% rear. So you do see some big differences among vehicles in the competition. And I'm not going to tell you that one is better or worse than the other, but it's important to know what that is. And it can be a tuning tool for your car. You can do some analysis, some simulation, and see the effects of that weight distribution. So how do you calculate weight distribution? You put the vehicle on 4 scales like shown over here, and you measure the weight of each corner of the vehicle, each wheel on the vehicle. The front distribution is the total front weight divided by the total vehicle weight times 100%. The rear is the total rear weight divided by the weight distribution times 100%. So that's a relatively straightforward calculation to do. You can also do the same thing for the left to right weight distribution. Again, that's not commonly done, and usually it is pretty close left to right, as in this example. You can also total up the weight, the total front weight, total rear weight, and the total weight of your vehicle, which is always good to know, right? You want to minimize the total weight of the vehicle. So by keeping track of that, that helps you focus on it. Okay, so why is the weight distribution so important? If you have a vehicle, I'm showing a bicycle model here, so I've condensed the left and right tires into one front tire and one rear tire. And if your center of gravity is not in the center of the vehicle, in this example, it's closer to the rear axle, so I have a higher weight distribution in the rear, then to react that cornering force and to keep the vehicle in balance, I'm going to need more force at the rear, more force from the rear tires. So with a rearward weight distribution, I'm going to require more cornering force from my rear tires. So it affects the balance of the vehicle, right? So that's why weight distribution front to rear is pretty important. The tires at the heavier end of the car need to produce more cornering force to balance the moments about the center of gravity. Okay, so why is that important? Well, because tires are very nonlinear with load. So I have a plot here of a Formula SAE tire. I have cornering stiffness, which is how many pounds of cornering force you get per degree of slip angle on my vertical axis. And then I have the load or the weight on the tire on the horizontal axis. And so using that example vehicle I showed a couple of slides ago, my front tires are at 118 pounds, which translates to a cornering stiffness of about 108.3. My rear tires have a higher load because I have a higher rear weight distribution. They have 148 pounds load on each tire, which correlates to about 115 pounds per degree. So even though I have a 30-pound difference between my front and rear tires, I only get a 6.5 pound per degree difference in cornering stiffness out of my tire. So I will need to have a higher slip angle in my rear tires to balance that out, to produce the force to balance the car, meaning my whole vehicle will be in a higher yaw angle or a higher side slip angle, if you use that term. So it directly impacts the handling of your car, the weight distribution does. Okay, so we typically, we will calculate weight distribution, but what you're really concerned with is the center of gravity location. And we do that in 3 dimensions or 3 axes, right? Typically, the x-axis is the center line of the vehicle. When we talk weight distribution, center of gravity location, we usually use the y-axis as being the center line of the front tires at the ground. And then the z-axis, the vertical axis, is the height above the ground. So your origin is right down here, the center of the car, the center of the front tires at the ground. And then we talk about the x location, the y location, and the z location of the center of gravity. And those are all important things to know for any analysis or modeling or simulation you're going to do on your vehicle. That's going to be a key input to your model or your analysis. So before we have our car built and we measure it, how can we calculate the center of gravity? Well, if you've got everything modeled in your CAD software, it can usually calculate that center of gravity location. But in reality, you typically don't have complete models of every part of the car in your CAD system. There'll be purchased parts. You'll have the engine or the motor, whatever, that you don't have that modeled in enough detail for your CAD system to figure its center of gravity. But you can weigh that part, and you can generally estimate or calculate where the center of gravity of the part is. So then you can do a calculation for your whole vehicle. So the center of gravity of the vehicle is the sum of all the part weights times their location divided by the sum of the weights. So you would actually do this calculation 3 times, once in X, once in Y, and once in Z. But it's obviously a very straightforward calculation. All you need to know is how much your parts weigh and where their center of gravity is located in the vehicle frame of reference. So here's a very simple and pretty incomplete example. I've got a car, I've got my front and rear wheel ends, including the knuckle and brakes and everything, and the wheel and tire. I've got one frame tube. I have here, I know its weight, its center of gravity location, and I have, let's say, the accumulator in the vehicle here. I know its weight and its center of gravity location, and I want to calculate where my center of gravity for the whole vehicle is. Well, it's pretty easy. You take the weight of each part here, this center of gravity location of those parts in X and Z, and you could do Y as well. And then you multiply the weight of the part by the center of gravity X location and by the center of gravity Z location. You sum those up, you get the total of the moment, the weight times the center of gravity, the total of the weight, divide those two, and you find the center of gravity location of your vehicle, which in this example is here at 1,000 millimeters X and just under 400 millimeters in Z. So it's a fairly straightforward calculation. The calculation is easy. Finding all the information and tracking the information to do the calculation is probably the harder part. So again, the calculation's simple, but you can create a spreadsheet to do it all for you. I would suggest you basically build your bill of materials, all the parts on your car. You can break it down by system or maybe by how you've organized your team, which sub-team is responsible for what parts. Enter all those parts in here, and it'll be a much longer list than what I'm showing here. The quantity of the parts, the weight of the part, how much of it is sprung, and the sprung column will generally be either 0 or 100 for most parts. There'll be a few parts that are 50%. And then where the center of gravity of that part is in your vehicle coordinates, right? Where it's placed in the vehicle, which you should know from your CAD system, or you should be able to estimate very, very precisely from your design information. And then you multiply the weight times these X, Y, and Z dimensions, total it all up, divide by the weight, and that will tell you where your center of gravity is. By tracking your percentage of sprung mass here, you can also add up what is your sprung mass of the vehicle. It's the weight times the percent sprung, sum that up. And you can do that by component group or by team, however you want to do it. And then you can also calculate that sprung to unsprung mass ratio. That's important. Now, I'm not going to give you a target number, but generally the higher that ratio is, the better your car will perform on a bumpy or rough track. Then you can add up the whole total mass of the vehicle and the center of gravity location for that vehicle. What is not in the chart is the driver. So a driver in a Formula SAE car is a pretty big part of the weight when the driver's in it. So that's important. You can take your driver weight and approximate the center of gravity as being basically the driver's hips, and then put that in your seat location in your vehicle. If you want to go into a lot more detail, in the book Race Car Design, it breaks the driver's body down into parts, so you can even put the driver in different positions, an upright position or a reclined position, and calculate the driver's center of gravity in more detail. You'd probably take another spreadsheet or a little separate calculation to figure out where the driver's center of gravity is based on your seating position, if you want to go into a lot more detail. Okay, so that's the mass, the center of gravity, and weight distribution. The other thing that is important are the moments of inertia in rotation of the whole vehicle. So typically we talk about the moments of inertia about the center of gravity of the vehicle. And there is yaw, which is rotation of the whole vehicle in cornering. There's pitch, which is the rotation about the y-axis. That's what happens in braking and acceleration. And there's roll that also happens in cornering, or possibly if you hit a one-wheel bump in the vehicle. So the formula we talked about for translation of the vehicle or linear motion is force equals mass times acceleration. To rotate it in yaw, pitch, or roll, the torque equals the inertia of the vehicle times the rotational acceleration. And there's going to be three terms here, one for yaw, one for pitch, one for roll. So again, to maximize that rotational acceleration, to make the vehicle respond as quickly as possible, you need to reduce the inertia or increase the torque. So today, again, we're going to focus on inertia. So So for Formula SAE cars and in the Formula SAE competition, the yaw rotation is the primary aspect of interest. The bounce and pitch moments of inertia are significant, but not nearly as important as yaw. Okay, so you can calculate it kind of similar to the center of gravity. Again, if you've got everything modeled in detail in your CAD software, it can do that calculation for you. Otherwise, you can use a spreadsheet, essentially the same spreadsheet, to calculate it. So the general formula is much like the center of gravity formula, only you use the square of the location of the part relative to the center of gravity. So it's really the square of the radius that your part is from the center of gravity. And strictly speaking, it's the mass of the part, not the weight. Again, they're as long as we compete on Earth, they're related by a factor of 9.81 in metric units. Okay, so we have the three axes, yaw, pitch, and roll. So there's three calculations that are very similar. And again, it's the distance of the part from the center of gravity location. So it's really the square root of the sum of the squares of that distance. But going back a slide, it's the square of the location. So you square that square root and you wind up with just the sum of the squares term. So you start with the inertia of the part in that direction. And for a lot of parts, the part inertia is not that significant, right? The inertia of a bolt is not that significant. So this is a lower priority, and sometimes for smaller parts can be ignored. But the mass of that part times the radius that it is from the center of gravity can be very significant because these are squared terms here. So you can calculate in roll and pitch, and again, yaw is the biggest concern of the three in Formula SAE. And then keep in mind that when you calculate the roll and pitch moment, you only want to use the mass of the sprung parts, since the unsprung parts won't be moving. So when you calculate yaw, you want to use the total mass of the vehicle, include the mass of all of the parts on the vehicle. So you can use that same spreadsheet I showed for calculating center of gravity and just add three more columns for the roll, or for the inertia in roll, pitch, and yaw. And that would be the weight of the part times the square of the CG locations, right, as shown in these previous equations, right? So you're just going to basically put these equations into these columns. Keep in mind the percent of the sprung weight for those, and also the inertia of the parts. That can be significant for some parts, that can be ignored for other parts. And again, you can calculate for your whole vehicle the inertias, and you can do the same thing. You can add the driver in. Again, you can just make the driver a point mass located in the center of the seat, or you can again refer to race car design and actually calculate the inertia of the driver depending on the seating position you're using. Okay, so now we've talked about the mass and inertia properties of the car as a whole. Another important part is the inertia of all of the rotating components in the drivetrain. So again, it's the previous methodology, right? How quickly you can accelerate your vehicle is determined by the force and the mass, right? But now we're talking rotational acceleration. So it's torque times the rotational inertia becomes a rotational equation. So the force that's available at, let's say, the rear wheels of the car to accelerate the vehicle is the torque from the engine or your electric motor times the gear reduction from your transmission or your chain drive or whatever drivetrain you're using, divided by the tire static loaded radius, basically the radius of the tire. So that's the force that's then available to accelerate your car. Let's say if you're accelerating in the acceleration bit. For braking, it's the opposite. It's the total brake torque you generate divided by the tire radius. That's the force available. But now this torque, the numerator in these equations, the torque that's available is reduced by the inertia of the parts times the acceleration of the parts, right? It takes some of that torque from your engine or from your brakes to spin up or slow down all of the rotating parts in the vehicle, right? So there is then less torque available to accelerate the vehicle at the ground, right? So you have to subtract off the rotational inertia times the rotational acceleration from that torque available. So the gear ratios also affect the inertia of the parts. A part that's on your engine, for example, let's say the flywheel, it's going to accelerate from 1,000 RPM to 6,000 RPM as you speed the engine up. But the wheels, if you've got a 5-to-1 ratio, they're only going to accelerate from 200 RPM to 3,000 RPM, right? So the amount of acceleration in those is reduced, and it's reduced by the square of the ratio. So you know your component inertia of your, let's say, your wheel and tire assembly, and you know the ratio back to the engine or the motor. You square that ratio, and that's the effective inertia, the inertia of the part divided by its ratio back to the engine or motor, whatever is driving it. Okay, so how do you find those rotational inertias? There's pretty simple calculations that will get you there. You're not going to have detail on every level of part. Calculating the inertia of a joint in your half shaft is not going to be exact. You're not going to be able to do a precise calculation for that, but you can use basically these three cases to come pretty close to make an effective calculation, right? So for a solid disc or a shaft, the inertia is the mass of the part times the radius of the part. Pretty simple. If you have a thin-walled cylinder, which might be the rim of your wheel, the inertia is approximately equal to the mass times the radius squared if your wall is thin, right? If you have a thick-walled cylinder, for instance, a shaft with a hole down the center of it, it's the 1/2 the mass times the difference of the square of the radii on your part there. So you can do simple calculations. You know, you're not going to be accurate out to the third decimal place, but they're accurate enough to do your calculations for your vehicle's performance, right? So then you have to convert that into an effective mass once you have your part inertias calculated. What we typically do is convert that into an effective mass that's added to the vehicle. Rather than separate out the rotational inertia, we convert it to a linear mass, a term that's going to be moved with the linear acceleration of the vehicle. So you take the inertias you calculated times the ratio to each one of those parts. The ratio to your drive sprocket is going to be different from your driven sprocket. So this is really a summation of several inertias times their ratios, and then divide by the tire radius again, and that gives you the effective mass of your car. So you would take, for the effective mass of the rotating parts, so you'd take the mass, the weight of your car, and add to it this effective mass that you've calculated. So it effectively makes your car heavier, and it will reduce its ability to brake or accelerate, right? Because you've effectively increased the mass of your vehicle. So again, you take the vehicle mass, what you measure on the scale, and you add this calculated effective mass to it, and that's the equivalent mass of your vehicle. That matters for your acceleration run, for your braking run, anytime you're moving the vehicle in the longitudinal direction. Okay, so far we've
Hey, Darrell, can I stop you?
Sure.
I did receive a question, and let me read it to you. How do we use the equivalent vehicle mass, which is vehicle mass plus effective mass, to inform design decisions we make on the car? Should we minimize the effective mass?
Yes, the simple answer is yes. Minimize effective and real mass of your vehicle, right? So if you wanted to try to predict your time in the acceleration run. You would know your engine torque or your motor torque and your drivetrain ratios and your tire radius. So you can convert that into your F equals MA, right, to get the acceleration of the vehicle. And your M term is then the combined mass of the vehicle and the effective mass. So that simplifies your calculations. You don't have to model all the rotating inertias. You can just add an equivalent mass to the weight of your vehicle. And then the same thing in braking, right? If you want to calculate your stopping distance, right, you would use the equivalent mass of the vehicle and the torque that your brakes produce and the radius of the tire that you're using for that.
Thanks, Darrell.
Okay. So now we've talked about calculating, and going back to that spreadsheet I showed a couple versions of, that can be a very, very powerful tool. You use it to calculate your center of gravity location and your inertia effects of the whole vehicle. But it also gets, right front and center in front of you, the weight of the vehicle, right? So it makes you more aware of the weight of the vehicle and components or subsystems, the weight of those, and it can help you track and reduce the weight of your vehicle. And my experience is when you have that spreadsheet in front of you, your car gets lighter and lighter because you're seeing those weights. And that's something you should review continuously throughout your design and development process, right? If for some reason the front suspension weighs twice what the rear suspension does, then that kind of alerts you to something's not quite right there. Maybe your data's bad, or maybe you've over-designed your front suspension, right? So it's a very useful tool. It's not just, well, now I know my center of gravity location and you walk away from it. It's a tool to use in designing and developing your vehicle. But at some point, you're going to actually have a vehicle, and you need to validate that with some physical measurements of the vehicle. So there's a couple of ways to measure your vehicle. Obviously, if you put it on your 4 scales here, you get your 4 corner weights. You can calculate your front to rear weight distribution and your side to side if you want to, but you can't, from just weighing it on scales, determine the height of your center of gravity here. So the first step would be to weigh your vehicle on flat level ground, and you will calculate, the wheelbase of the vehicle. You can calculate the location of the center of gravity. Your front and rear tire radiuses, loaded radiuses. Then to calculate or to measure the center of gravity height, the typical way is to use your same scales and raise one end of the car higher than the other and look at the weights on the scales again. So by knowing the angle you raise the car to and the new scale readings for the front and rear, you can then calculate the height of the center of gravity here from those measurements. So the formula, and I won't go into deriving it and detailing it all out. This is the formula. You can calculate the height from the front and rear, from the rear weights here, the A dimension, where the CG is relative to the front, the wheelbase of the vehicle, the total weight of the vehicle, the angle here, the tangent of the angle you raise the vehicle to, and the radius of the front and rear tires. Fairly straightforward. I would recommend you look up this SAE paper here. It goes into the development of this formula, how it's derived, and some ways to determine how accurate your measurements are. Obviously, the higher this angle, the more you elevate one end of the car, the more accurate your calculation will be, the more accurate your data will be to plug into this equation. So it's a pretty good read. And just in case I made any typos putting this in here, it might be a good idea to double check me by going through this SAE paper. So highly recommend looking into that. Okay, so that's how you would measure your center of gravity location.
Hey,
so
Darrell.
Want to measure? Yeah.
I received a few more questions on the effective mass.
Okay.
It's a 2-part one. What about cornering cases with a combined longitudinal and lateral component? Should we still consider the effective mass? And then how about pure lateral? It's also a question.
I'll answer the easy question first. In pure lateral, it doesn't really matter because you are not accelerating those parts of the vehicle, right? You're not speeding up your wheels or tires. Any of the rotating stuff would be at a steady state condition in cornering. So you would just use the vehicle mass there. In combined cornering and acceleration, you can probably, again, just use the vehicle mass. You're not going to be at your maximum acceleration, right? So while you're in a corner, so the torque from your engine is much less constrained by the inertia of the drivetrain, right? You're not subtracting as much torque from your engine power, right? You're not accelerating all those rotating parts as much. You're not accelerating them in rotation as much. So this term becomes much smaller, and your combined lateral and longitudinal acceleration will be tire limited, not engine torque limited, or I guess torque at the wheel limited. So I would say in both those cases, the safe assumption is just to use the vehicle mass. You might be a little bit off, especially if you're in a very large radius turn and you are accelerating relatively hard. You could probably even proportion it, right, for how much longitudinal acceleration you're using versus how much lateral acceleration. Something kind of like a friction circle approach. So hopefully that answers those questions. Is any other questions, Matt?
Nope, that's it. Thank you.
Okay. All right, so we talked measuring your center of gravity location. What about measuring your rotational inertia? The most common way you see, if you Google, it will talk about a trifilar pendulum, which has 3 cables or wires or strings, whatever you want to call them, and a circular platform. You turn that platform and you let it oscillate, and by timing the oscillation, you can calculate the inertia, and it would be the inertia of this platform plus the inertia of whatever you put on top of it. So you would first measure the inertia of just the platform with nothing on it, then place your part on it, measure the combined inertia, subtract off the platform inertia to get your part inertia. If you were going to measure the yaw inertia of your entire car, this would kind of be the way to do it. You would have a very large platform, big enough to park your car on, and some pretty robust cables to suspend it from, and something pretty strong to hold the weight up and let it turn. But you can do very good yaw inertia calculations, and this would be a lot of work involved. So I don't recommend trying to measure the yaw inertia of your car, although it's a straightforward thing to do. It's just a challenge to make all the fixturing and support it properly. So for most of your rotating parts, your wheels, tires, brake rotors, half shafts, sprockets, that sort of thing, since those parts are all symmetrical about their axis of rotation, you can use a simpler pendulum, a bifilar or 2-string pendulum. And this is something I did a lot of when I was building mini Baja cars in college. You can make a fairly simple pendulum. You need some kind of place to attach it, and then a couple of strings, only 2 strings, and then make a fixture that has a shaft on it that mates to the shaft that goes into your sprocket, for example, or that will mate to the wheel hub on your wheel and tire. So that has a couple of advantages. It automatically centers the part on the measurement fixture, and the part is guaranteed to rotate about its axis of rotation, right? So you can do that, makes a much simpler fixture. And the formula is here, pretty straightforward. The inertia, the total inertia of the part of the pendulum plus the part is the mass times gravity, or the weight, times the square of the period of oscillation, times the square of the span of the 2 strings, divided by 4 pi squared times the length of the strings. And then you can separate that out. That's the total inertia of the pendulum plus the part. So you subtract the pendulum inertia from the total and you get the inertia of your part. Pretty straightforward. A couple of caveats. In practice, you want this L dimension to be much longer than the width here. I ran out of slide space, so I have a nearly square pendulum, but you want the length to be longer. And by having the length of your cables longer, it also reduces the period of oscillation, so it's easier for you to time that. And what we typically do is you let the part rotate for 10 oscillations, you time 10 oscillations, and then divide that by 10 to get the average oscillation time. That way, if you're off by a couple of hundredths of a second in timing it, then when you divide by 10, you're only off by a couple of thousandths of a second. So it makes it a little more accurate. But this is a pretty simple thing to construct. You can very effectively measure the inertia of all of your rotating components. And by using a shaft that it pilots on, it automatically centers things and you don't have to worry too much about getting things correct. Theoretically, you want exactly the same load in these two strings. So by centering your part on the pendulum, it makes it very easy to achieve that or come very close to having the same weight on your two cables. Okay, so that pretty much wraps up the presentation. So just to summarize this, you want to minimize the mass and the inertia to get the maximum performance out of your vehicle in braking and acceleration and in transient cornering, right? When you go from straight to turning into a turn, that yaw mass or yaw inertia is important. Minimizing that will make the car transition much quicker. There are several important criteria: the sprung weight or sprung mass, unsprung weight, the weight distribution, and the center of gravity location, both in X, Y, or in X, Y, and Z. All three are important vehicle properties. You can calculate them, and then you can actually measure them. Pretty straightforward once you have a vehicle. Early on, when you're designing your vehicle, you can calculate those. That will feed your performance calculations and simulations. Later on, when you have a vehicle, you can measure them to get accurate results or realistic results. Moments of inertia, again, particularly in yaw, are important in the handling of your vehicle. You can, again, calculate them pretty well from basically the same information you use to do your center of gravity calculations. A little bit harder to measure the yaw moment of inertia of your vehicle. It can be done, and using a trifilar pendulum is not the only way to do that. There are other methods. Then in terms of acceleration and braking, the inertia of individual rotating parts in the vehicle is pretty important. You can approximate those from simple calculations, and then you can measure them very, very simply with that bifilar pendulum, or there are other methods to use. And again, you can pretty easily measure the critical parts in your shop. I think virtually every team will have 4-wheel scales. You just need some means to elevate 2 of those scales to measure center of gravity height. And that bifilar pendulum is something you can easily make from some scrap materials in your shop. Okay, so that wraps it up. A few references. There's a couple of standards for terminology. Those are, I didn't refer directly to those, but they're useful to know. That book, Race Car Design by Derek Seward, has some really kind of hard to find information on weights of the drivers and weight distribution. It breaks the driver's body down into the different components so you can place them in different positions and calculate the weight and the inertia of the driver if you want to. Again, the SAE paper that talks about how to calculate center of gravity height using 4-wheel scales. And then there's an interesting article in Race Tech magazine that talks about, from a practical sense, reducing the weight of your car. And then a couple of websites, I guess, for a trifilar pendulum, and then using a bifilar pendulum. You can look those up. All right, so that wraps up my part. Any additional questions, Matt?
Thanks, Darrell. while I'll give another minute for people to put some questions into the chat, I do have a few. So is there a certain area of what you described today that you see that troubles most teams or have trouble with explaining during design judging presentation?
I think a lot of them do not follow the simple spreadsheet, right? Their car weight comes out to be whatever the weight comes out to be, and they haven't really understood where the weight comes from, what systems, what components. And a lot of times they don't have appreciation for the center of gravity height, right? They'll have relatively heavy parts located up high in their vehicle that could readily be located lower in the vehicle, right? So I think my advice would be create that spreadsheet early on, and it will be a living document, right? You'll add parts to it, you'll take parts away from it, you'll change the weights of parts, you'll change the locations of parts, you may change the driver location, right? But those are critical performance targets, right? To have your center of gravity height, your total weight, and your front to rear weight distribution. And it's simple. It's maybe a little tedious to keep that spreadsheet up to date, but it's not difficult work. And by tracking that throughout your design process, you'll be way ahead when you get your vehicle built and start to develop the handling of your vehicle.
Okay, thank you. Just one more reminder, if you have any questions, please put them in the chat, and I will tell them to Darrell. Besides the calculation sheet, is there, do you know if there is a preferred method that the design judges are looking for, that they'd like to review this data in detail besides that sheet that we reviewed?
No, I think, a summary, start out with a summary of your vehicle. What is the weight distribution front to rear? And that will basically tell you that at the competition when we do the official weighing of your vehicle. And hopefully that is not a big surprise to you when we weigh it at the competition. It may be a little bit different from what you weighed on your scales in your shop, but the weight distribution shouldn't be radically different. On a pound per pound or kilogram per kilogram basis, it might shift a little bit. And then from there, know what drove that, right? If you have a bunch of aero, if you have a big rear wing with movable elements, right? Be aware that raised your center of gravity. And as a judge, I might say, what was the trade-off there, right? You gained some downforce, but you raised your center of gravity. And you put a motor up there to rotate your flaps to give you less drag in a straight line. What was the trade-off for the weight of that motor being mounted up high on your rear wing? So that's the kind of thing I look for as a design judge is, do you really understand all of these things, and have you considered the trade-offs and made a good trade-off, a good compromise between weight and center of gravity location and performance of your vehicle, right? The lower center of gravity is a very, very basic first principle of your vehicle, right? You want the center of gravity to be as low as possible in the vehicle, but there are, like everything else, there are compromises to be made. So do you know what those compromises are, and have you understood them, and can you justify them?
Okay.
I think that's what most of design judges would look for.
All right. I received a question, Darrell. If we notice that the metrics like our center of gravity is different in real life compared to our goal, what steps or methods should we take to address the discrepancy?
First of all, I would double check all the data in my spreadsheet. Are all the parts listed there, and are all the dimensions of the part, the locations of the part correct? So again, it's a very simple calculation. There's not a lot of room for error there. It's a simple calculation. It's the input data that matters, right? You're basically just adding and multiplying numbers. So if you have a radical difference, you've got a number different, whether it's a weight number or a location number, right? It's pretty simple. It might be a little bit hard to track, to figure out which number is wrong in this big spreadsheet. And again, it's a pretty simple spreadsheet, but it will become big, right? You need to have every part identified in there and the location of every part identified. And you will probably see bigger variation if you do measure the inertia of your vehicle, because you're not going to have inertia for the inertia of the individual part, right? For some of the larger parts, it's important to have that for say your engine and transmission assembly. You need to figure out the inertia of that part, which is not going to be a trivial thing, right? You're going to have to break it down into different pieces and calculate the inertia of different parts of it. So that's always going to be an estimate, and there's always some room for error in that estimate, unless you go to a lot of trouble to measure the inertia using something like that trifilar pendulum. So inertias will be a little tougher to accurately calculate. And again, the calculation is simple. It's the information that feeds that calculation that's more challenging.
Okay. Thank you very much for that. I'll give the participants one more minute here to put in any questions. I don't have any more. All right. Well, Darrell, if you could go to the next slide. Thank you very much. I would like just to say quick follow-ups. Please remember to join us for our next virtual event on Friday, November 10th. It's the Formula SAE Aerodynamics Design Overview by going to the SAE-Detroit.org webpage and clicking on the register button. Thank you to all of our participants for joining our overview today, and a special thank you to today's presenter, Darrell Hancock Jr., the SAE Detroit section staff, as well as the SAE Carolina staff for their involvement in putting together today's presentation. If you have any questions or inquiries about this presentation, please email the SAE Detroit section staff at events@SAE-Detroit.org, shown on the screen. If you're watching this on YouTube, please consider liking this video, sharing it with someone who might find it useful, or in subscribing to our SAE Detroit section YouTube channel. Have a great day, everyone.
Thanks, Matt.
Thank you.